Hello, Assalamualaikum, and welcome back to today's lecture. So now we will go through the second example when it comes to the translational mechanical systems. But before that, let me just inform you that aside from translational mechanical systems, there is also rotational mechanical systems, which I will not cover personally, but I will direct you to a YouTube video that covers one of the specific examples in this book, okay, so that you can learn how they solve the rotational mechanical systems by yourself, okay. And then I will also give you one homework based on this one, which is translational mechanical systems, that you need to submit before our next lecture, which is after Raya lah. Okay, so just to give you a heads up, because this mechanical system is very important, because it will be covered, a lot of it will be covered in test 1 and maybe a bit in the final exam. Okay, so you need to be quite proficient in how to translate these real world systems into transfer function. Okay, so going into this specific example 2.17, we looked at the instruction is we need to find the transfer function x2s over fs for the system in 2.17a. So this time we have two blocks of mass, which is m1 and m2, and there is a single force Ft pushing on m1, pushing it to the right, and then we have these two displacement, which is x1t for mass 1 and x2t for mass 2. Okay, the system has in total 3 springs and 1 viscous dampener. New to here is the friction coefficient. Here introduce Fv1 and Fv2, which is the friction coefficient, which is the force that resists, one of the forces that will resist the force of Ft. Okay, and we need to find the transfer function as shown in 2.17b, Fv3s plus K2 over delta. So this one I will explain in detail what is delta and all that. Okay, firstly, to create this transfer function, since this is a 2 degree of freedom mechanical system, we need two equations of motion. Okay, and we also need to consider, to do that, we need to have this consideration where we for example, we hold m2, the mass on the right, we hold m2, and then we push m1 to the right following the Ft direction. Get the equation for that. And we also need to hold m1, and then for example, for m1 you need to be able to move m1, hold m2, and then you also need to consider the movement when you hold m1 and you move m2. Okay, so you do that to get the both of the equation of motion. Okay, we'll go through it right now. So, also I should mention that let's look at this. The system has 2 degrees of freedom, since each mass can be moved in the horizontal direction while the other is held still. Thus, 2 simultaneous equations of motion will be required to describe the system. The 2 equations come from free body diagrams for each mass, and superposition is used to draw the free body diagrams. Okay, so you can read that, but I'll show you in the free body diagram how to do that. Okay, give me a second. Okay, so for the first one, we have a situation where we have this block, this mass, M1. Okay, so just now in the first example, I drew the free body diagram in the time domain. And then once we got the equation, I changed it to frequency domain with Laplace transform. Here, I'm just going to straight ahead do it in frequency domain. So if you look at the let's draw the setup again just now, where we have a wall here, and then we have a spring. You have the block of M1, and then we have a viscous damper, and we have another spring. Then we have another block M2, and we have another spring here to the wall. Okay, and like I said, now we have a new force to consider, which is friction. FV1, FV2, and the damper is the FV3. We have the K1 for the spring on the left, and K3 for the spring on the right, and K2. Okay, so for M1, oh, I forgot to draw the FT. So FT is here. And we have the displacement X1 T. We have the displacement X2 T. Okay, so firstly we have the force Fs, Ft, which will become Fs, pushing the block of M1 to the right. So this is Fs. Okay, and then when we push that to the right, we have all of the other forces will move in the opposite direction. Okay, firstly let's go for the mass inertia. So the mass inertia will go in the opposite direction with a mass of M1, and in Laplace, once we do Laplace transform, we have this. Okay, that's the inertia. And then we also have, because we are pushing the M1 to the right, we have the pulling effect from the spring of K1. So we have another force here of K1 XS. Okay, and then lastly we have the friction from the bottom of the mass, which is given as FV1 S XS. So I should mention that these are the first free body diagram is for when you move M1 and you hold M2. Okay, so you hold M1, you move M1, you hold M2, you'll get this free body diagram. So again, when you push M1 to the right, you have the effect of the damper, the one in between, pushing in the opposite direction. So this is FV3 S X1S, and also the effect of the spring K2 X1S. So these are this is the free body diagram for M1 only due to the motion of M1. Okay, where the movement of M2 is not taken into consideration. So let me just write this again. M1 move, M2 hold. So you get this free body diagram. So next, let's consider what happens when we hold M1. So M1 hold, and then M2, you move it. What are the effects on M1? So going look back upstairs here. So when you move M2 to the right, the immediate movement is caused by the viscous damper, FV3, and the spring of K2. Okay, so that is what will affect the motion of M1. So we have this, the damper, which is FV3S X2S. Okay, remember now, because it is caused by the motion of M2, so it's X2S. And now we have the K2 X2S. Okay, so to get the total forces that is acting on M1, okay, the equation of motion for M1 only, we need to combine all of these free body diagram into one. Okay, so you combine them into one. So this is where you write all of the forces that is acting on it. So just combine all of them. Oh. So you have K1, K2, X1S. You have FV1 plus FV3 S X1S. Okay, going to the same direction. And then you have the pushing force Fs, and we have the initial force M1 S squared X1S. Okay, M1. Okay, and on the opposite side we have the effects of movement of M2, which gives you K2 X2S and FV3 S X2S. Okay, so these are all the forces that are acting on M1.